Okay, now let's try to simplify a radical expression. A radical expression is the same as, we're talking about radical as a square root in this case, with an even exponent. Okay, so now I've got a coefficient and then a variable part, right? So we can work these both. We can identify this as 50, right? Square root of 50 is the square root of x to the 6th. And if you remember, 50 is the square root of 2 times 25, if you recognize that there's a perfect square in there. And you can recognize square root of x to the 6th as square root of x to the 3rd times x to the 3rd, right? 3 plus 3 gives me 6 if we remember our exponent rules. So now we have a perfect square. That's 25. And we have two of these, the x cubed. So the 25 can come out as 5 times 5, right? So we have 5 on the outside times the square root of 2. And this x cubed, square root of x cubed, is simply x cubed. So I'm going to rewrite that as 5x cubed times the square root of 2. Remember, I had also told you that anything with an even exponent is a perfect square, right? So, and you simply divide the exponent by 2. So even exponents are perfect squares. So you can divide the exponent by 2. So if I take the square root of 50 x to the 6th, again I knew that this was 2 times 25 times x to the 6th, the square root of all that. So this is a perfect square. X to the 6th is a perfect square. This comes out, 25 comes out as 5 times 5, right? And then I can divide the exponent by 2, so I just have 6 divided by 2 gives me x cubed. That comes out. And then I'm left with just the square root of 2, with 2 on the inside. All right, so either way I come up with the same answer. Let's try simplifying the square root of 18a to the 12th. Okay, so again we can take a look at our two parts separately here, right? And we can rewrite 18. We know one of the factors is a perfect square. It's 9. So 2 times 9 gives me 18. And I know that anything with an even exponent is a perfect square, right? So that's, I'm going to go ahead and write a to the 12th. So we have 9 is a perfect square, and a to the 12th is a perfect square. If I take the square root of this, I'm going to have the square root of 2 times the square root of 9 times the square root of a to the 12th. Right? So we know that the square root of 9 is just 3. And then the square root of a to the 12th, I simply take 12 and I divide that by 2. So I'm left with a, the exponent, to the 6th. Right? So you can think of a to the 12th divided by 2. And that's how I get a to the 6th. And over here I still have the square root of 2. So my answer, and it's convention that I'm going to put everything that's outside of the square root in front of the square root expression. So I have 3a to the 6th times the square root of 2. Okay? And just as a note, again, just a review, if you didn't notice that there was a perfect square in there, and instead you broke down 18 into, say, 3 times 6, and you think, uh-oh, I'm stuck, I don't have a perfect square in there. Remember, let's break down the 6 into a 2 times a 3. So I can rewrite that as 2 times 3 times 3 times a to the 12th. And then I have 2 3's, so one of those can come out, right? I have 3 and 3. And I also know that my a to the 12th is a perfect square because it has an even exponent, and I can just simply divide that exponent by 2. So this means that my 2 stays on the inside. the 3's come out, one of the 3's comes out with 2 inside there, and I divide my exponent by 2, so I get a to the 6th, and I get 3a to the 6th times the square root of 2. So remember, even if you don't recognize those perfect squares, you can always break it down into your prime factors, and you can figure out what pairs you have. But it helps a lot if you can get more comfortable with knowing your perfect squares, and then you can recognize them as factors.